A week ago or so, I heard about this low resource text classification, a parameter free classification method with compressors paper, where they claimed to beat BERT on sentiment analysis classification. Now, once in a while, I see something and I am just absolutely compelled to try for myself, and this was one of those times. It has everything. It's simple, it's fast, it's easy to implement, and it's one of my favorite machine learning algorithms, k-nearest neighbors. I sometimes do contracting and consulting work for clients, and the number of times I've had to tell somebody that their problem really doesn't require deep learning or neural networks is substantial. So when I see something super simple like this, doing text classification for sentiment analysis with k-nearest neighbors for the classification and Gzip for the compression distances, which is kind of being used as your feature vectors, I really just have to try that for myself. The research paper itself also came with code that is on GitHub, but it seems to have a bunch of extra tweaks and techniques for getting the most performance out of things, and I really just wanted to try something super simple. This concept is very easy to implement and test, and I really just wanted to confirm that I actually understood how this actually works, because this idea of compressed distances as features sounds simple, but also a bit strange. So if you're a little fuzzy on what the heck this is or what's actually happening in this paper, maybe you even saw this paper, basically what we're going to be doing is a from scratch example of it here. Now, you should already know up to this point what k-nearest neighbors is. I do have an older tutorial on it where we actually build k-nearest neighbors from scratch. I'll put a link to that in the description. Now, with that out of the way, to get started, we're going to import Gzip for the compression, k-nearest neighbor from sklearn for the classifier, and pickle for our dataset. I've pre-built a couple of datasets just to keep things simple and moving quickly. Next, we'll load the dataset and split it into train and test groups. I'll start us off with the 500 sample dataset to start, just to keep things going relatively fast. Samples are text strings that are paired with a label of -1 for negative sentiment or 1 for positive sentiment. If you want to try this on your own data, go ahead and feel free. I just took one of the movie reviews datasets to do this with, but there's lots of sentiment analysis datasets, or maybe you have your own that you want to try. So feel free to do this with anything else. You just need to match string to a numerical label. It doesn't have to be -1 and +1. It could be 0 and 1, for example, as well. So we can check out our first sample's text and the sample sentiment, and as you can see, just what I've described. Machine learning models don't work with text, though. We need to represent text in some way numerically instead, and somehow make that a feature that a model could theoretically fit to. The proposal is that we compress and use this NCD, or normalized compression distances. Okay, what's that? Well, first we need to compress the text, something like this. Now, that doesn't look like any number to me, and instead we're going to need to convert that to a number by taking the length of the compressed text. We can't just use the size of the compressed text because that's not normalized and easily comparable to other examples. We want to normalize it so that we can compare the distances between two compressed texts and essentially the entire dataset. So we'd grab the length of another compressed sample, and then we'll do this to the combined strings, so x plus x2. All right, so we have a number, but it's not normalized. So we'll set the value to be the combined sample compression length minus the lesser of the two sample compressed lengths divided by the largest of the two sample compressed lengths. Wonderful. That looks like a good number to me. Now, we want to actually do this with every sample in the dataset, and every sample needs to be compared to every other sample. So our NCD function will look like this. Now we'll compute the NCD for all training samples. All right, so let's see an example of a sample now. So we have 501 total samples. Why 501 and not 500? I don't want to talk about my logic right now. We allocated 401 to training and the other 100 to testing in this case. You can see here for the first sample, all the distances are 0.8 to 0.9s, but we can even compare it to itself, as we will, and you can see it is extremely close. The only reason for any distance at all is how we're calculating this NCD. So each sample is a vector of 401 normalized compression distances, and we'll do the same thing against the test data. Notice that here we're calculating the normalized compression distances between the testing samples and the training samples. Now, this is not like data leakage or anything like that where you're leaking like the labels. We're comparing it to the training samples because that is what the model is going to be trained on. It's going to be expecting, okay, what's the NCD to these values, because that's what the features are. And then later, when you would go to actually deploy this into the wild, so to speak, you would do the same. Every sample would be compared to every sample in the training set to build this vector of normalized compression distances that is the feature set that you are going to be predicting on. All right, so with that, we're ready to train a classifier, apparently. As is typical with k-nearest neighbors, feel free to tinker with the number of neighbors. The original paper was using 2, I believe. I found 2 to be too variable, but there are just so many factors to consider here, and you're welcome to try various k values here. As you can see and note by speeds, the slowest part of this algorithm is actually the computing of the NCDs. The actual k-nearest neighbors classification is particularly fast, even especially on just 500 samples. We will address the NCD calculation speed shortly, but more importantly, how did we do? Okay, so we're not quite beating BERT, but we're not doing terribly either, terribly being anything close to 50%, which would just be random. We're also not using any fancy techniques. We're just using k-nearest neighbors with Gzip and calculating these normalized compression distances, and we're using only 500 samples. And we did it in 25 lines of code. I want to take a moment here to really appreciate what the heck is going on. We're compressing text and comparing those compressions and assuming that similarly sentimented strings are going to compress with similar lengths due to statistical techniques that are going to be used to efficiently compress. And that's it. Essentially just common speech patterns for angry people and for happy people. That's the entire algorithm, and we're just doing k-nearest neighbors on that. I sat on this paper in my subsequent work with this for a few days because it really just felt like it had to be wrong. And it was, at least in part, in the original paper. The author made a mistake of using k equals 2 for the neighbors, and whenever there was a tie, it was calculated as correct without any tiebreaker being run. I guess he should have followed my k-nearest neighbors from scratch tutorial. This error caused about a 5% difference in accuracy, in that reported accuracy in the paper, which was enough for this method to no longer do what the paper claimed, which was actually beat BERT, a popular transformer model that is indeed used for things like sentiment analysis. And my personal results are even worse than the papers, but this is due to, I think, my simplistic methods. I think I'm calculating NCD different and all that. And the fact that with my methods we're at 70% accuracy with, again, only 500 samples up to this point, even that alone, I really just want to stress how absolutely staggering that is to me, that is even possible, that there is something there for these for k-nearest neighbors to nibble on and make some progress. I still can't believe it. And yes, I sat on this because I feel like there's got to be a problem, and I didn't really want to release a video on this because something has to be wrong here. And I still suspect there is, and maybe someone can point it out and get us back to what I believe should be the worthy accuracy for this model, which is likely 50%. Now, on the flip side, what actually is going on here, right? I can logically think through why normalized compression distances might work for comparing strings in some ways. But I would imagine with a large enough data set, you'd have total convergence on lengths of compressions, and everything would be the same distance from everything else on average in terms of sentiment. You would have just as many positives and just as many negatives. Gzip the compression algorithm being used here is a statistically based compression algorithm. Why would the lengths of compressions be sufficient enough to classify sentiment? It's not these normalized compression distances alone. Each sample is compared essentially to every other sample as a vector, and then these vectors are all compared. So I suppose in some grand scheme, if there are enough similarities, the lengths will vary on average just enough by common syntax and words used to potentially be able to classify sentiment based on like those patterns. But still, I don't know, man. That just seems wrong. It just doesn't. It seems flawed. Yes, there will be patterns, but then it would be different if we were comparing those patterns in like a tokenized way or something like that. But we are literally just comparing the lengths of those compressions. Come on. So in my tests, accuracy does vary significantly by sampled data at 500 samples. So anything from 60 to 80% depending on the chosen samples. It flattens out at about 10,000 samples fairly reliably for me, around the mid-70s in percent accuracy. But before we show 10,000 samples, calculating normalized compression distances linearly like this will take hours. We can do better, and we really need to. So to begin, the starting lines through the definition of NCD calc are basically all the same. We just need to import multiprocessing. We'll also specify the number of processes to use, which will depend on the CPU in your machine. Next, we know we want to parallelize this process, and how we might do that can obviously vary. We are going to calculate NCD for every single sample, and for every single sample against every single sample, right? So the normalized compression distance, add each sample against each sample. No calculation there depends on any other calculation in the process, but it is absolutely imperative that the order of the samples and the NCD vector for each sample is maintained. To do this, we're going to use multiprocessing's pool to calculate those NCD vector values. But if we just did this and appended the values to the list, even if we initiated the pools in order, we'd still have no guarantee that the order of the samples would be maintained, as some processes might actually finish before others. To handle for that, we're going to first initialize the NCD matrices with zeros, and then we'll update them according to their respective indice in that sample, basically their sample index. Next, we'll specify a helper function that calculates the NCDs for a given sample, and then we'll use pool to map that function to all samples. Now we create the pool and calculate the values. So now we know for each index the vector of NCD values, so then we can populate them into those zeroed matrices. Then finally we can train and test the classifier. And then we can also confirm, based on this exact same data set, that it is the same accuracy as before. So it does look like, at least up to this point, our logic works. Now let's run this all together and use the 10,000 sample data set. 75.7% accuracy is not bad at all for such a simple method. That is very cool to me. It's still less accuracy than the original paper's authors, so it'd be worth looking into their methods and seeing kind of what they did differently, and maybe even help to inform you of some ideas about how to even further improve this method in general. It might also be a function of the data set that I use. I just used a movie review data set. I think it's from Stanford. I can't even remember. But there's definitely better data sets, I'm sure. And then a more homogeneous data set would also probably work best. So where every sample is more or less about the same starting length. And then I bet just based on that factor alone, you could eke out more performance. But again, I was trying my best to use the fairest, most, let's say, realistic data set that I could get my hands on. Now, all of that said, the next question is, okay, how might we actually use this method in practice? Sure, we can train and get a certain accuracy, but then how would we actually use this model in practice? Essentially, it's the same as any other sample. you're going to take your input string, you're going to compress it, you're going to compare the distances to every other sample in the training set. And then we'll pass that through k-nearest neighbors to determine if it has more positive or negative sentiment neighbors based on that NCD vector, and then we'll classify it as such. I have two example samples. One is a positive and one is negative. So for a sample, you might have it defined like this, and then we compress. Then we calculate the NCD vector for this sample, which is the calculation of NCDs between this sample and every other sample in the training set. Notably, we could also multi-process here as well, but it's fast enough for me for a single sample. And then if you wanted to batch samples, you would just use the exact same logic that we used in the training. Anyway, after doing that, we can then pass it to the classifier, and in this case, the prediction is a positive sentiment. 1 is positive, -1 is negative. We can try the negative sentiment string, and yep, that works. That said, this method being 75% accurate is going to make a lot of mistakes, and I also think there's a sweet spot for sample string length. Anything that is outside the norm in length for training data is likely, almost certainly, going to be I don't know the right word, but misclassified. So even if it gets the prediction right, it gets it right for the wrong reasons. And anything too short to benefit from statistical techniques for compression will also probably not work well. So for example, here's some short strings, and we can see that these are all classified negatively. I would say these are all misclassified. Even if one of them is correct, it doesn't really matter. Not for the right reasons. It's just always going to be negative based on purely the length alone. We can further inspect this theory by graphing a histogram of the sample lengths. And then we can kind of zoom in here more specifically for a 0 to 1500 length. And we can just clearly see that we want at least 200 plus characters. And that's characters and this is not a compression length. This is quite literally the original sample. So at least 200 characters, but really more like 600 or more to work well with our training data. Out of pure curiosity, I also tried dimension reduction and principal component analysis, and none of this really yielded anything that appeared to show any value between these normalized compression distance vectors, but I really wouldn't have expected them to either. That said, somewhere apparently in those 401 dimensions or in the 8001 dimensions in the 10K sample, there is something for k-nearest neighbor. There is something for k-nearest neighbor. Oh my gosh. There is something for k-nearest neighbors to get a nibble on. Overall, I think this serves as a really good reminder that other algorithms do exist besides just deep learning, and it can be fruitful to visit first principles once in a while. I hope you've enjoyed this tutorial. I'm still in disbelief that it works. Like I said, I can think of lots of reasons why this wouldn't work, and all of that. But even in the argument of, sample lengths outside the norm, as long as there's enough samples at some specific length, it still probably is going to work. And that said, I am still just in disbelief that it works as well as it does. I might expect, 60% accuracy or something like that. Just a slight edge I could understand. But the fact that it has such a solid edge, is shocking. It really is shocking. Working on this really brought back a lot of nostalgia for me, as NLP and k-nearest neighbors were some of my very first early projects in programming in general. So yeah, if you've enjoyed this in-depth look here, then you might also enjoy the Neural Networks from Scratch book by myself and Daniel Kukiewa, which teaches you how to program neural networks truly from scratch without any deep learning frameworks. You can check that out for yourself at nnfs.io, and otherwise I will see you all in another video.